Okay, so thank you very much. My name is Jiang Kan. Also, you can call me Michael. I'm so sorry I cannot be with you physically, but I'm with you, spiritually. All right, so let's start, okay? So in this work, we focus on tracking small and fast-moving ball. If we can track these balls accurately, it gives us a lot of high-level useful information, such as to understand the player's play pattern or to understand the sequence of events happening in the video. So this problem can be formulated as such. Given the input, a short broadcast video clip, we want to output the ball XY position at each time step. Assume there's only one ball in this video clip. But the ball is small, and often there are false detections due to ball-like objects. For example, these are the examples. And often, ball is misdetected due to image blurry, for example, these examples, or due to occlusion. For example, the ball now is behind the player, so it's not visible, or due to complex background, like these 4 cases. And on top of that, the ball trajectory is not completely predictable due to bouncing or hitting. So we have studied quite a lot of existing work and tried to determine whether their ideas or their techniques can be used in our work. So the traditional computer vision-based ball tracking algorithm typically suggests that first try to detect the moving blobs and then try to classify these blobs as true ball candidates or false ball candidates using features such as shape, size, color, location. After that, combine these ball candidates into small tracklets to check if it agrees with some predefined motion model. And the most commonly used motion model for ball tracking is the constant acceleration motion model. And then connecting these tracklets together to form an overall long trajectory. So in nowadays, most of the detection work has been replaced by the deep neural nets. To detect the small objects like a ball, some suggest to zoom into part of the image, crop it so that make the ball more obvious. And some suggest to scale in the feature map. For example, take an input image, let it go through the convolutional neural net. At the end of the CNN, we have a feature map which represents the information in the original image, but it is in a small dimension. So using skip connection, using deconvolution, we can upscale this feature map to a much larger scale. And from this large scale feature map, it's easier to detect small objects like ball. Then there are also others to suggest that why not make use of the temporal correlations obviously exists in the connecting frames. TrackNet is one of such examples. They suggest to stack 3 images together to form a 9-channel spatial image and let it go through the normal convolutional neural network and the deconvolutional neural net layers to detect the ball position. Ball detector is never perfect. There always exists false ball or misdetections. Hence, we are always dealing noisy detection. So given a sequence of noisy detection, if we know the ball follows a certain predefined motion model, then we should be able to track this ball more accurately. And this can be done using the Kalman filter. At each time step, the estimated ball state is represented by a Gaussian distribution. The mean represents the most likely ball state, and the covariance represents the uncertainty. And following the predefined motion model, we can then predict what is the ball state in the next time step. And in this next time step prediction, the covariance is increased due to a noise term in the motion model, because we know the motion model is never perfect. And then using the detection, we can update this ball state. This is the posterior. If there is a false detection, usually the false detections are far away from the predicted ball state, hence it can be rejected. If there is misdetection, then we have to carry forward by just using the predicted ball state into the next step. And moving balls may not only follow just one motion model. So it is helpful to use multi-motion models to track the ball. In this work called interactive multi-motion model, they suggest that the ball state, instead of using a single Gaussian distribution, they suggest to use a Gaussian mixture. For example, this green one represents the ball state according to a constant acceleration motion model, while the blue one represents the ball state according to a sudden change motion model. And we know the transition probabilities between these motion models by counting the historical data. For example, if the ball is traveling in this constant acceleration model, the historical data shows that 80% of the probabilities in the next time step, the ball is still stay in this motion model. 20% of the probability switch to the different motion model, and so on. So with this transition matrix, we can obtain a new Gaussian mixture. And following our motion models, then we can predict the ball state accordingly. And then given the detection, we can now update each motion model as well as their weights in the Gaussian mixture. However, there's one problem in this algorithm. Suppose that the true ball is here and the false ball is very close, and it appears to be a better candidate in this time step. And if we follow this, we track on the wrong object, then in the next step, we are still tracking on the wrong object. So it can be dangerous. So this problem can be alleviated by another algorithm called Viterbi algorithm. Suppose initially the ball is anywhere in this oval. And in this time step, we have two ball detections marked by these plus signs. And then plus a misdetection case. So in this time step, altogether, we have 3 hypotheses of the ball states. Although the motion model seems to suggest that this is the better ones among the 3, but the Viterbi algorithm requires us to keep track all hypotheses, don't discard it just yet. And going on to the next step, when we have the true ball detected, and this information can help us to correct the false hypothesis in the previous step, because this is less likely a track compared to this according to our motion models. And since we are processing the recorded video, we can use future informations to improve the estimations at the current time step. Suppose at time step t, due to misdetection, we are not very certain where the ball is, so the covariance is large. Then in the T+1, due to the correct ball detection, we are quite certain where the ball is. And this information can be used to backtrack to get a better estimation of the ball states in the time step T as indicated by this red oval. So having considered all the related works, we suggested a framework which consists of two visual-based ball detectors and one motion-based ball tracker. And in these slides, we've just focused on the two visual-based ball detector. The first ball detector is a single frame ball detector. Here, we reuse, or more precisely, we retrain Facebook's general purpose object detection model called the Detectron 2. Why we choose them, we retrain them, is because they have this, they called a feature map pyramid network, which is able to upsample the feature map from low resolution to a large scale. That helps us to detect the ball, small ball. And if we cannot detect the ball using this single frame ball detector, we have to use our three frame ball detector. And in this three frame ball detector, we use the single frame ball detector as a feature extractor. So for each of these image, we obtain the large scale feature map, and then we just stack these three feature map together to amplify the feature map. So in order to detect the ball, which is hard to see in a single frame. And then in our motion-based tracker, ball tracker, we integrated all the techniques we have introduced earlier so that the motion-based ball tracker can fill in the ball position when there is a misdetection or filter out wrong detections and select the globally most likely ball track by using Viterbi algorithm and backtrack using the future informations to improve the estimations at the current time step. And such a motion-based ball tracker significantly improves the tracking accuracy. Our experiment shows that if our ball detector can detect 93% of the ball, then plus this combined with this motion-based ball tracker, now we can track 99% of the ball. And as an ablation study, we apply this tracker onto other ball detectors, poorer, less performant ball detectors, such as the TrackNet in our video. It can only detect 87% of the ball initially, but combined with this tracker, now we can detect 96.5% of the balls. So here is a demo for tracking the tennis ball, and we achieved more than 99% of the accuracy. And here is example of tracking the soccer ball. Here we use a thin circle to indicate the uncertainty. The uncertainty will grow when there is a continuous occlusion, as shown in this part of the video, because it's occluded consecutively. So that's all for my presentation. Thank you very much for giving me this opportunity to share this work, and I would like to hear your comments and the feedback. Thank you very much. I don't hear anything.
Okay, how about now? Can you hear something?
Michael. Hi,
Oh,
Michael.
yes, I can hear you, Masome. Hi, Dr. Masome.
We miss you here, Michael.
Yes, I too miss all of you. So sorry due to my teaching load. I was busy preparing for my next semester.
Yeah, very nice presentation. And I mean, just as a comment,
Yes.
we like to audience, we actually use Michael's tracker to track the cricket ball. It's very nice and easy, transferable to other sport. This tracker is fabulous. Is really helping us with tracking the ball. It does do a little bit more smoothing than the trajectory of the ball requires. But my question is, like, I know this is just one single object tracking. What would it take to do multi-object tracking with the same kind of approach?
Yes, very good question. In fact, I spent some time thinking about that. I think one of the critical step is in this case. So as a single object tracking, all we have to do is just select the most likely object and use that detections to update the uh, ball states. But for multiple object tracking, first of all, we have multiple track and we have multiple candidates. There are some algorithms such like Hungarian algorithm, which should be able to help us to do a globally optimized assignment, assign the candidates to the most likely track. So I think we need to add in that step so that we can track multiple objects. Other components, I think more or less is the same.
Right. Okay, so looking forward to seeing the multi-object tracking as well, because that's very, very applicable. Thank you very much.
Sure, yeah.
Anybody else, any questions? Michael, I work on badminton, so I use
Yeah.
the track or shuttlecock. Then there are a lot of coordinates. Sometimes you have the shuttlecock trajectory missing.
That's right.
So have you applied for shuttlecocks? Have you tried your algorithm?
Yes. I think tracking shuttlecock is indeed very challenging. So our experience shows that for the overall solutions to work well, we need a strong detector as well as a strong tracker, the motion-based tracker. So the detector performance is very important. If we use our very strong ball detector tennis, we can track 99%. But if we use other poor performance tracker, because they start with 87%, that means there's a lot of misdetection and there's a lot of false detection. And with too much misdetection and false detection, even our tracking algorithm will fail. So it really it needs to be a combination of both a strong detector and a strong tracker. And particularly for the badminton, I think the detecting part is really difficult because the badminton travels even faster than the tennis, and the shuttlecock is so small. Often it is just blur like a line. So it's indeed very, very difficult. I think we can work together. I cannot promise that I can solve your problem, but I really like to work with you together. So perhaps just give us some of your videos. We try to tune some of our parameters. See whether we can help to make it better. Yeah.
Anybody else? Any questions? None. Thank you very much, Michael. I'll contact you.
Sure. Thank you very much. Thank you.